Here is an explanation for the answer to final exam question number 90 in Electronics Demystified 2nd edition. If you have the printed book, you'll find it on page 437. We're talking here about a well-designed straight ZEP antenna in free space. We can expect it to operate at a certain fundamental frequency and also some of the harmonics. And as it works out, we can expect it to operate at the fundamental and all of the harmonics. In this diagram, the ZEP antenna is the lower antenna design here. It is an end-fed, half wavelength of wire, usually fed with 1/4 wavelength of open wire transmission line. I made a video just yesterday, that would be May 2013, May 2013. I made a video explaining the operation of a ZEP antenna in a little more detail because some people have trouble understanding how an antenna can be fed at the end and actually work. You'll find it under my Mysteries and Musings playlist in my video channel. But this is the basic design of a ZEP right here, and I'm comparing it with a half-wave open dipole antenna, which is the same half wavelength of wire fed in the center instead of the end. Well, there are certain advantages to feeding an antenna like this at the end, and there are certain disadvantages. One of the advantages is that it operates at all of the harmonics of the fundamental frequency. That is, here in this question, choice C. It'll operate at the second harmonic, that's twice the fundamental, the third harmonic, 3 times the fundamental, and so on. Now, an ordinary half-wave open dipole will only operate at the odd harmonics of the fundamental. You get a current distribution on a half wavelength wire that looks something like that at the fundamental frequency. Half of a wavelength, as you can see, the current is maximum at the center and minimum or near zero actually at the ends. So you're feeding it at what is called a current loop. With a ZEP antenna, you get the same current distribution along the wire, but you're feeding it at a current node, which is very close to zero current. Theoretically, out here, the current is zero. Here, it's going to be almost, it's very close to zero. So this is where people get some trouble understanding how a ZEP can actually work, because you're getting an antenna to accept power at a point where there's practically no current flowing. How can that happen? How can a wire actually accept power when there's no current flowing at the feed point? I explained that in that other video I was mentioning about the theory of a ZEP antenna. But anyway, here's the half wavelength current distribution, and actually it goes up and down standing wave, as they call it. At the second harmonic, you would get 2 of these waves. In fact, we can cut that in half like that, duplicate it, invert it, and show you how the current is distributed at the second harmonic on a ZEP antenna, something like that. It becomes a full wavelength wire instead of just a half wavelength. So that description doesn't apply anymore. Becomes a full wavelength. At the third harmonic, it will become a 1 1/2 wavelength wire, and you would get 3 of these current loops. At the fourth harmonic, you would get 4 current loops, or 2 complete cycles, but you always get a resonant condition, and you always get pretty much the same feed point impedance. which, as it turns out, is going to be a very high, purely resistive impedance. Very high, hundreds of ohms, maybe even over 1,000 ohms if the wire is very thin and this thing is in unobstructed space. So you're going to have a high standing wave ratio on this transmission line, so it's important that it have a low loss. Again, it doesn't have to be exactly 1/4 of a wavelength long. You can make this transmission line longer than 1/4 of a wavelength. It's not recommended that you make it shorter and then use a transmatch or an antenna tuner. You're always going to need that because of the high standing wave ratio on this transmission line. But again, the correct choice for this question is choice C. A ZEP antenna will work at the fundamental frequency and all of the harmonics.